It is the day 3. In the last 2 sessions, we have discussed the basics of R programming, and we have started from the mean, median, the data types, and then we are getting into the quartiles, box plot, the rest of the statistical parameters, and then we get into the statistical hypothesis testing. We just left with the ANOVA over there, and then we have to discuss correlation and regression. So let us start with the ANOVA. In the last session, we have discussed the t-test, one sample t-test and 2 samples t-test. And in fact, this ANOVA is almost a continuation of such a t-tests, and we have to continue. So this is the tentative schedule, and there are many tests available, and the most prominently used tests are t-test, ANOVA, especially to compare the variability, it is f-test. The people are concentrating more on t-test and ANOVA. Even we call it as a student t-test, right? So it is because, see, there are 2 groups available. There are 2 groups available, and there are 2 groups available. Now, the question is whether these two groups comes from the same population. Okay, let it come from the same population, whether it is normal or not. Okay, let it be normal. We are finding the averages of the groups, variances, that and all. Now the question is whether the average is same or not. Whether the average is same or not. Say, for example, in the first one, we may get 35 as the average. In the second set, we may get 40 as the average. So the average is not same. Again, the question rises whether such a difference is admissible or not. If the difference is within the admissible limit, we can accept, and if it is not, we will not accept. So that's the criteria we are moving, and especially it is to compare the means, arithmetic means. Okay, fine. So in order to do that, either we may go ahead with mean. In ANOVA, actually, we will be using f-test. In order to assess the error points, we are going for the f-test since it compares the variability. Okay. The same idea is applicable, but if we are dealing with the categorical variable, then we have to go for the chi-square test. And if you are predicting a variable, that is our forecasting, then that will become with the regression. So these are the few famous tests we have to execute before. Actually, the regression is the last one. Before getting into that, we have to do all these tests in order to validate, in order to check whether our data is perfectly matching for the forecasting, and whether the forecasting will give us the better results. Actually, the idea is to get into the correlation and the regression and the multivariables, but whether it is matching with the requirements is the question. That is what we dealt in the last 2 classes. And now it is with the ANOVA. Of course, we can do with the t-test. The t-test is for 2 variables. This will compare more than 2, 3, 4 groups. Even if you are able to do with the for loops, then you can do very few t-tests. But the problem is, if we are executing the t-test many times, you have to compare the results of all the t-tests, and once again that become an issue for us, because our objective is to reduce that work. Now, this ANOVA tells us whether there is significant difference between or within any groups. That's all. But this never tells us the groups are entirely different. It will tell, is there any difference? That's all. Yeah, there is a difference. That's all. Okay. So the usual question is, see, suppose I am getting the insignificant. How to interpret this? How to rectify that? Then there are some other tests. The post-hoc tests are available. We have to get into that. Okay. So this is a generalization of the t-test. If you are, there are two types of ANOVA, the one-way ANOVA and the two-way ANOVA. Of course, there are many available factorial designs, MCOVA, those are all available. Here we restricted with one-way and the two-way. Even of course, the one-way is also used to compare the several means, but the number of independent variable is only one. Number of independent variable is only one. See, suppose we are writing y is equal to f of x. This y is called dependent variable, and this x is called the independent variable. Whereas in the computer language, they will call it as the predictor and the response variable. So the variance in the dependent variable once again has two parts. We have drawn like that. So the first cluster and the second cluster. So here, whether the variance, the differences are between the groups or it is within the groups. So those two items we have. The ANOVA value is the ratio between the within the groups and between the groups, and we are using the F ratio because we are finding the variances. So we are using the F test, and this F ratio should always be greater than 1. In such a way, we have to manage our formula. Okay, so the reason for ANOVA is to compare 3 more samples. You can compare any number of groups simultaneously, whereas in the t-test you have to do it many times. I gave that drawback already. If you are using with the for loops, that the t-test, then you have to compare the means many times, and once again that become a much manual work for us. Okay. So the assumptions are more important in the ANOVA. The populations should be obtained from a normal distribution, or at least it should be approximately normally distributed. The samples must be independent of each other. Usually we will check for the first one, but we will not check for the second one. We will come back to that after the completion of the program. And the variances of the populations must be equal. And in F test we are using the variances. So the ANOVA hypothesis become all the means are equal, and the alternate hypothesis is at least one of the mean is different from others. Understand that it is not saying all the means are different, but it is saying at least one average is different. At least one average is different. That's the idea. So actually this is the formula to get ANOVA. So the F calculated value is between the groups, the variance square divided by the variance of within the groups. And for between the groups, here is the rule, summation ni into xi minus, this is the grand mean, divided by k minus 1, where this w, this is within the groups, This is in I minus 1 by in I minus 1 with si power 2 in the numerator. These are just the rules. Let us go ahead with the problem. A researcher wishes to try 3 different techniques to lower the blood pressure. Okay, so he is trying to reduce the blood pressure. The subjects are randomly taken. There are 3 groups, and the first group has instrumented with medication. The second is with exercise, and the third one is with diet, some special diet. So after 4 weeks, they are checking the reduction in the blood pressure, and they have the data. They have the data, and here it is. And now they are claiming there is no difference between the averages of medication, exercise, and diet. They find the differences. Say X1 is medication, X2 is exercise, and X3 is diet. They find the average. Here the average is 11.8, 3.8, and 7.6. And now we have to say, is there any difference between these averages or not? That is, the averages between the medication, exercise, and diet are same or different. Of course, the value might be different, but we have to say statistically whether that is that error is acceptable or not. That error is acceptable or not. So manually what we have to do, we have to find the total x1 power 2, x2 power 2, x3 power 2. We have to find this total, and the averages, the variances, everything we have to calculate, and we have to apply in these rules. And finally we have to get our f value. After getting the f value, we have to check with the table value of table value at a 5% level, whatever that you are deciding, 3.89, here it is. After finding this f value, we have to check whether it is 3.89, above 3.89 or below 3.89. Then we can say whether our null hypothesis is accepted or not, or whichever is possible. Now we are going to execute through program. We are going to execute this program. Okay. Fine. So here the medication, exercise, and the diet 3 are given. 3 are given. So here the number of columns are 3, and we are taking it as k, and the total number of items here, the total number of items 1, 2, 3, 4, 5. So 3 into 5, 15 items are there, and alpha is 0.05, and here we mentioned it as 5%. The degree of freedom, actually I should not say here as a numerator and the denominator, as I know the answers already. I just put numerator and denominator for the better understanding. So here it is k minus 1, here k is 3, it is 3 minus 1, and the denominator here is n minus k, and the total number of items is 15, and the k value is 3, so 15 minus 3 is 12. Now what is this degrees of freedom? The degrees of freedom is the number of items we can calculate independently. Say for example 2 plus 3 plus 5 plus dash is equal to 15. Then this is the only number I can calculate, but these are the numbers here. These values are independent, where this number is purely depending on the previous values, and hence the degrees of freedom here is k minus 1. and here it is. So this is the way we are calculating. It is we have to find the grand mean. This is the total value, the sum of all these values, the sum of all these totals, and divided by the total number of items, and we are getting the average, that is the grand average, and then we have to minus this xi minus grand total. The xi values are here it is 11.8, 11 point, sorry, where is it? Yeah, here 11.8, 3.8, and 7.6 with the whole square divided by k minus 1, and then um, we have to calculate. I'm just going through the manual calculation so that with the ANOVA summary we can. And we have to find for the within the groups also SW power 2. This is with the 5.7, 10.2, and 10.3 average. Here it is SI power 2. Here it is 4 numbers, 4 numbers, 4 numbers, because there are totally 5. So 5 minus 1. Totally 5 elements are there. Totally 5 elements are there. So 5 minus 1, 4. Fine. And we have to find this value. Finally, we will divide. We have to divide. Even we can write SW power 2 by SB power 2 also, if it is greater than 1. If it is less than 1, we should not use them. Simply say whichever is higher, we have to put it in the numerator. And we are getting the F calculated value based on this value, based on the CV value, the critical value. We can decide whether it is accepted or not, or what is the difference. Now this is 9.17. This 9.17 is greater than the given set point 3.89. This is greater than 3.89. In fact, too much deviated. So what we will say, there is a significant difference between the averages of these groups, and you can find, see here it is 11.8, it is 3.8, this is 3.8 and 7.6. Idea whether that much error is acceptable or not. Okay, so the conclusion is at least one of the mean is different from others. One of the mean is different from others. Fine. So we are going to do in a program. Let us open the new one here, and see, this is my data. This is my data. First, we have to initialize our vector. First, we have to initialize our vector. Say, for example, I am keeping y1. We have to key in our numbers 12, 9, 15, 3, 10, 12, 9, 15, 3. Yeah, 68320. 68320. Yeah. 591248. Yeah. Okay. So I initialized these values and I run. I checked for any initialization errors. It is no. So I'm just making all in a single row, single vector. So y1, y2, comma y3. So let me check how it look like. So this is y, and I'm just making it in a row, single raw data. And now I want to assign the groups So I want to generate my n. In there are 5 entries in 3 groups. There are 5 entries in 3 groups. 1, 2, 3, 4, 5. 5. So in 3 groups. So this n is what I am doing. I am repeating this 1 to 3. This 1 to 3. Sorry, I am repeating 5 3 times. Or even I can write like this also. It doesn't matter. C of 5 comma 5 comma 5 like this also I can write. Repeat 5 comma 3. So if I print this n, you will get 3 5s. So you will get 3 5s. Okay. Now I want to make my groups. This group is the repeat of 1, 2, 3. That many number of times. Whatever you have generated. So I am making it as a group. Let me print this. 1 1 1 1 1 5 times, 2 2 2 2 2 5 times, and 3 3 3 3 3 5 times. Okay. If you are thinking directly that how to do that, it is always a better way to create n and then to create the groups. That's the best way. Otherwise, if you club directly within the group to generate the numbers, that will become once again the function, the composition of rules. Of course, we can do, but that will affect the line by line command. So let us go ahead with our data. We have, let me put it as a data frame. The data frame, we discussed that in the first class. If you create it as a table, we cannot access the elements from the table, whereas if you make it as a data frame, we can access the individual elements. So the first one is y. This is my data, and I made it as a group. Group is equal to factor of the groups, because we are making it as a factors, but unfortunately we have not discussed that part. Groups not found. Yeah, it's a group, right? Yes. Now I am printing my dat. So now what will be having, this 10 will be assigned to 1, 12 will be assigned to 1, 9 will be assigned to 1. Like that, we assign the numbers with the groups. Now, we are fitting. Actually, we are going for the linear fit. LM is the function, linear model. LM is linear model. So we are going for the LM function, LM of y with the tilde symbol group. So here it is what you want to predict, and here it is the independent variables, comma for my data. Yes, it is rand. I want to check what is my fit. So I am giving print fit. Actually, all the prints are, that one is just to see what is this. That's all. We have to go for ANOVA. So I am making it as ANOVA. See, once you type, you can see this ANOVA within the brackets, within the curly brackets, set brackets, it is stats, which means that this ANOVA belongs to that stats package. This command ANOVA belongs to stats package. So this ANOVA of fit. Yes. Now we got our result. Now we got our result. Okay. So here the analysis of variance table, it is given response y, my response variable is y, groups and residuals, right? So the first one, k minus 1, we have seen, like k minus 1 we have seen, right? The degrees of freedom, k minus 1, that is 2. The second one, n minus k, it is 12. So here it is 2 and 12. The sum of the squares, 92.190, is it? Yeah, if we, yeah, it is 160.13 and 92, I'm sorry, 92.133 and 160.800. This is the mean square is 46 and 13, and the f value is given as f value 3.43, whereas the p value here is 0.06. The 0.06 is greater than 0.05, so we will reject this at for 5% level. That is, the null hypothesis is rejected, which means that there is a significant difference between the means of that is the averages of these groups. Okay, here it is showing the significant codes. Here it is showing the significant codes. See, this is 0. 0 means triple star, 0.001 double star, 0.01 1%, single star, 0.05 dot, 0.1, and it will be with a this up faced code and down faced code for 1. Here it is showing with the dot. It is showing with the dot. This dot means at a 5% level it is significant. So you don't want to give any significance level in the ANOVA. Directly from the ANOVA fit we can get into that. That is at which percentage it is significant. Fine. So this is the way we are using our ANOVA model. Let me save it. ANOVA model. Okay. Fine. So now we have our data and we are keying. If you want to make some other data, the data sets are available. The data sets are available in the R program. Of course, in the Python also it is available. There are many data sets here. Ability, air miles, passenger, all these are the free data sets you can use for your analysis or for your practice, everything. These are data sets we can use. See, this many data sets are available. Okay. So now let us generate a general ANOVA, just a general one. Say for example, this is x1, x1 with the R norm. So here I am not typing any values. I am going for the normal distribution. I want to generate 10 with my mean is equal to 0 and standard deviation is equal to 1. So the next one is x2. It is with the standard deviation 1.5, and the next one will be 3, and mean is equal to some 2 with the standard deviation 1. So we are running these 3, and I am making my x. X is C of x1, comma x2, comma x3. Let us run this, and if you print your x, you will be getting the values of x. You will be getting the values of x. So we have to make our group. The group is, say for example, I am typing group 1. We are using group 1. It is C of repeat, right? 1, comma 10, repeat, 2, comma 10, comma repeat, 3, comma 10. I want, because here I generated 10 values, here I generated 10 values, here I generated 10 values. So I want to repeat 1 10 times, 2 10 times, 3 10 times. That's it. Now I want to make it as a factor to accumulate with my data. So the same group 1, the same I am making as factor of my group. Yes. Can we do ANOVA directly? Yes, it is possible. AOV is the command. Yes, it came. Thank God. The formula. Making some x as the operator, or some x4. X4 is the response, and here it is what created group 1. Group 1. Yeah, x3. Model with the variable lengths differ for this is or now with the 10, 0, 1, 10 value, 0, 2, 0, 2. X3 with the group. No. AOV is the command we used it. This is the formula. Data is null, projections fine. Can I get group 1 here? Typing group 1. Yeah, I'm getting my group 1. A1. AOV is the command for ANOVA. AOV command also we can do. AOV. I want to predict my yeah, fine. To predict my x with the group 1. Yes, it's not x3, right? I created that x vector here. I want to predict my x. That's why it is showing the variable lengths differ. This is my value. That's why with the x and the group it is showing the variable lengths differ. Okay, so I want to print to my A1. Print to my A1. Yeah, here it has shown AOV we used it. So here it is the same sum of the squares, degrees of freedom. You can see the small difference in the result. Group 1 and the residuals, actually it's like a transpose. Here it is the residual standard error, it is showing this much error it has. The estimated fx may be unbalanced, which means that it's not equal. Those are not of equal. Okay. Now here we used ANOVA. Here we used the ANOVA command, and here used the AOV command, right? If you go for AOV, this AOV belongs to stats, and this ANOVA belongs to ANOVA also belongs to stats. So there are many other packages also giving such a ANOVA results. And there are many statistical results. See, all these are based on the packages, and many have written packages. The R consists of thousands and thousands of, which more than 10,000 packages are available. So many researchers have created their own package, their own program for their own requirements, and so the command name also might differ, and it is with respect to the package. And even we can say this is one of the disadvantages of our programming, because today we will be practicing this R programming with the ANOVA, and tomorrow there might be many updates, and many might give uh, various new updates, new packages, and there they might give uh, various easy methods also. And it is practically not possible to be familiar with all those 10,000 packages. We can be with a very few only. But the CRAN R website from where we have downloaded the R program is really a wonderful one. We can go ahead with it. Whenever they are uploading the new packages or the updates and all, they are giving the newsletters over there. Even we can subscribe that also. From there we can download. From there we can download. Let me check. Say for example, this is FDTH package. This package is FDTH. After 2021 only, they distributed this package. But if you use this package, then you can do almost all the statistical works, and even creation of the frequency distribution tables, histograms, and there are many we can do. But if you see the program, the base program is same only what we have done, but they made it as a simplest manner, and they have given that as a command to us. So directly if we use the command, it will access the particular package, and it will show you the enhanced result. It is like how we are holding our camera separately earlier, whereas now it is with mobile phones. Now it is with the mobile phones. Okay. So let's come back to the presentation once again. The program for the previous problem, yes it is. And the two other problems are also given. If necessary, we can get into that, and we have to get into the correlation. See, the correlation and regression plays a very vital role in the analysis. So the correlation gives you, see the name itself, it is correlation. So the increase in one variable with respect to the increase in the another variable. So if we have taken a point, this is x1 and this is y1. If we have taken another point, then this is x2 and this is y2. Whereas by considering these 2 points, say for example p1 and p2, the x value has increased and also the y value. On the other hand, if you have the data like this, say for example this is y1 and x1, and this will be x2 and y2 with the points p1 and p2 with the x and y axis, then here the x increased, whereas the y value decreased from y1 to y2. So the influence of one variable with the other variable. That is what this correlation gives us. If one variable increases, the another variable will, what is the effect will be on the another variable. So the increase in one variable gives the increase in the another variable gives you the positive correlation. The increase in one variable gives the decrease in the another variable is called a negative correlation. If there is no such a relationship, it will be zero correlation. If and there are perfect correlation, perfect negative correlation, you will be having the intermediate correlations of 0.5s. That also. This is with the positive correlation. This is with the negative correlation, as we explained in this diagram. This is with the zero correlation, no relationship at all. So now, is there any assumption for the correlation? If they have given any data, can we find the correlation? No, we cannot. The relationship between the groups, the variables what we have taken should be linear, and the multivariate normality should be there. Even if you are taking many, if you are taking many variables also, everything should be normally distributed. Multicollinearity should not be there. Simply say one variable cannot be the scalar multiplication of the other variable, and there should not be any autocorrelation. We'll get back to that later. And homozydicity should not be there. We will come back to that point later at the end. So the correlation is usually highly applicable in the psychological studies, educational tests, but there is a huge controversy here. I will come back to that one also. Reliability, validity, data items, whether the data is consistent with the hypothesis. Usually, the correlation is used to propose the hypothesis also. If you find the correlation and getting such a relationship, then only we can frame the hypothesis. Whether there is no difference, is there any strong difference there? Less than greater than that part and all, we can frame your hypothesis. Okay, so before predicting, we should get the basic knowledge, and there are many other tests also, like our discriminant factor analysis. When COVA is there, right? To isolate the influencing variables. Say, for example, suppose we are having 10. Suppose we have a huge data, a normalized data, and we have many variables which is contributing to our data. Among these, all these variables are contributing equally, whereas only one variable is contributing much to the data. Even we can say extremals. I'm just saying for that, even we can say extremals, contributing much to the data. This is usually happening at all the places, even in the working places also. Few persons may show the tremendous records, and the rest of the persons will show their normal, usual outputs. But even that tremendous data also, it is not possible always. Maybe at that will become a separate clusters, and that will be, say for example, in semester 1, semester 2, semester 3 separately you can. Now, this kind of correlation we have to, this kind of calculations we have to, and let me write the rule for the correlation. This is, I am writing the direct one. So n into summation xi yi minus summation xi into summation yi, the whole divided by square root of n into summation xi power 2 minus summation xi whole power 2 with a square root of n into summation yi power 2 minus summation yi whole power 2. So here, after this is called the Karl-Piazon coefficient of correlation. The Karl-Piazon coefficient of correlation. There are another two correlations also. One is Kendall correlation and another one is Spearman's rank correlation. So whenever you have that interval level of data, you can go for the correlation there also, no problem at all, provided you can go for the Spearman's correlation. Okay. Now, let us actually the command is very simple to find a correlation in the R program. The command is just COR. That's all. Let's get into that. Say for example, let me take these two, then we will get into the next. This is y1 and y2. I initialized these values already. I want to find the correlation, so the command is correlation of y1 comma y2. y1 comma y2. You will be getting your correlation value. Fine. So we can go for the correlation significant test also. We can, if you are going for such a significance with the many values. Even you can have many groups of values, like say here we have given this cluster, right? Here in this cluster, let me take in this cluster, even what you can do, you can make these three as a subcluster and these two as a subcluster. With these clusters also, you can find the correlation coefficients to check is there any significant differences. Okay, so here the p-value is 0.4. So there is no difference. Sorry, there is a significant difference between these two correlations. Actually, it's not equal to 0. This is not equal to 0. Actually, the difference, right? The difference is not equal to 0, and there is a high correlation. And here the correlation is 0.5 almost. 0.5 almost. Fine. So now, how to visualize this correlation? How to visualize this correlation? For the visualization, actually, I am using this package. This is repository Cranon. I am using Corplot, this package, CORRPLOT. I am using this package, CORRPLOT, this package. You can install this package. I already installed, so I am not installing that. Here, I am calling this library Corplot. I am using Corplot, library Corplot, and I am using the MTCOS dataset because I want to show the diagram. I want many variables, so let me go ahead with the MTCOS dataset. This is the inbuilt dataset in R. So here you can see these are the data. See, for example, Mazda, MPG, cylinder, display, HP, drought, weight, Q second, versus AM, gear, carburetor, everything it will give you. Even you can go to help, you can type MTCOS, right? And you can get the data, that is how many data are there, what is there, who has provided this, what are the descriptions of those variables, right? What are the calculations behind that, everything that you can get. Okay, So it is with empty cos. Now let me take my data. Hmm. My data is with empty cos cell. In this empty cos, I want all with say for example 1, 3, 4, 5, 6, 7. It is there here 1, 3, 4, 5, 6, 7. Actually here and all it is only with 0 and 1 name. This is 0 and 1 name. So we will be getting a different diagram. Hence I have chosen only these three. Now see here how I use it. I put a comma here, which I put a comma here. See, suppose I am typing empty cost within the square bracket 2 comma 3. Empty cost with 2 comma 3, it is 160. 160, which means that 1, 2 comma 3 I have written, right? 2. In 2, it is 1, 2, 3. It is a matrix structure, so it is 2 comma 3. So it is 2 comma 3. Here I want all these, that is in the columns I want all these I want, whereas in all these columns 1, 3, 4, 5, 6, 7, whereas in the column I want row I want all, whereas in the row I want all. That is why here it is empty, comma, and then C. Okay. So usually whenever we are writing the program, we will miss this comma and we may not be getting the answer as desired. Okay. So even you can see this is head of my data. You can see that the head usually will give you the first 6, 1, 2, 3, 4, 5, 6, first 3, 6, just for a glance, just for a glance, just for the glance, just to look the data, just to look the data. Okay, so even you can change this also. If you write then this will give you the first 8 data. Usually by default head is giving 6. If you want to change anything, even if you can give 2 also, that will give you only the first 2 data. Fine. So now I'm going for my result. I'm going for my result. I'm going to find the correlation. Going to find the correlation. For what I want to find? I want to find correlation for my data. I want to find the correlation of my data. My data we have already given, right, for everything. Okay. So let me run this and print this res. This res. If you print this res, you will be getting a correlation matrix. You will be getting a correlation matrix. You will be getting a correlation matrix. And make it so. If you use the round command, this will be with only 2 digits. You can the rest of the manipulations that you can do, doesn't matter. So it is with round. You can do that. Fine. Even you can use RCOR, that one also. Okay, we will come back to that part later. RCORR is also there. Now we have to visualize our data, right? So what I am doing, I'm using car plot. I'm using car plot. CORRPLOT, car plot. I want for res. That's all. I want for res. That is result. My result. I am running this. I'm running this. It should come. Thank God it came. So this is the correlation diagram of this result. See, for example, between this MPG and the MPG, it is 1. MPG and MPG, it is 1. That is with the same variable, it will be 1. And blue colors are 1, and the high red colors are -1, and that will be varying. That will be varying with respect to the color, and the same color with the size also will vary. Fine. Now, now you can use the same car plot for the result, and type is equal to, you can give upper. If you give upper, you will be getting only the upper side, and if you give lower, you will be getting only at the lower side, the lower triangular matrix. Actually, these upper triangular and lower triangular are the mathematical concepts, the Gaussian Gauss methods, and they used that method to display the correlations. In fact, the underlying method is Gauss method. Now, that by default it will be circles. Okay, so what I am giving, method is equal to circle. Default it will be circle. I am giving method is equal to circle. So all these will become in terms of a circle. Now I am changing this to SQU. I am changing this to square. You can get in terms of squares, and you can make it as a ellipse, and this will be showing in terms of ellipse. What is pi we have? You can make it as a pie chart. See, for example, the percentage will be shown in the pie chart. So here, see, MPG, with the MPG it is 100%. The correlation is 1, so it is 100%. So it will be here. So here it is around 90%. So here it will be around 90%. So 90% will be minus. So it will be in the red color. And what else we can do? We can look for some color. Thank God it is with square once again, if it is color, and shade. Yes, for this one later. If you made that the square boxes, if you have given shade, you will be getting some sort of shades, that lines for the negatively correlated one, not for the positively correlated. And even you can customize that. Finally, you can make it with the number. Yeah, I missed that. You can make it with the numbers. I'm sorry about that. I should do that first. You can make it with the numbers. Yeah, it is with the numbers. So you will be getting the full correlation matrix in terms of a number, even with the same thing, from -1 to +1 limit, with the same colors, with the different variations. Fine. One more, if you see here, it is MPG, disp, HP, dot, everything is same, so you can do that. I'm just doing this. Take anything, number, no problem. I have to give that in the quotes. Number. Color, tilde dot color. I'm making it as black. So what will happen? This red color, this MPG, disp, HP, dot, these and all shown in the red color earlier. This was shown in the red color, and now it is in the black color. You can change the colors also, and you can do many customization. Say, for example, TL dot SRT. If you do that, say I'm giving some 45 means degree. 45 degree I am giving. Then you can that label will be with 45 degree of angular rotation. That and all you can do. And say, okay, now another question: how to know all these parameters? To know all these parameters, what we have to do? If you find, say, it is by reference only, it is from internet. I also get this from internet. from the references, I went to the CRAN. I used to visit the CRAN website frequently. That is one of the very good website actually. They have done much. Um, they will update the packages also. So at our free time, just we have to open and see the package. Once we get some sort of familiarity, at that time we will came to know. Just it's having a look is enough. Having a look is enough. At that time, we will came to know, yeah, we have struggled this much to create our frequency distribution, whereas here it is this much easy with a single line. Say for example, FD, they have created the frequency distribution. So like that and all, it will be there. They will give what are the parameters has to be given, and what are the other restrictions, limitations, that and all will be mentioned website. So from there you can get, even from here also, if you go for the help, even everywhere. Suppose if you are going for this MT course, you can go see the note. This is the reference. This is the reference. Okay. Suppose I am typing some car plot. Let me type the same one, car plot. You can see all these examples. Many you can get it from here. Even instead of going to ORCRAN, if we know the package and if it is really applicable for you, even we can get into this help also. Directly we can do it here. Directly we can do it from here. Okay. Fine. So, in fact, there is another package. Let me type with this. Is there anything with this? My result. I want to check for my result. Yeah, correlation of my result. Significance test. Okay. So regarding this correlation and projecting it differently, getting various interpretations, there is one package called HMISC. Yeah, it's there, HMISC. This package is one another excellent package for correlation. Very good package for the correlation. And there are many other points also with the HMISC you can explore with that. Fine. And the another one is library with performance analytics. The performance analytics is one another package. I'm giving you another. See, in the first two sessions, we have given most of the advantages of our program, but it has many disadvantages also. See here, in order to install this package or to call this package, it has the base packages as XDS, Zoo, the base. See, this is from base package. It will take a graphics, everything. But this package created under the version R version 4.1.3. The R version is 4.1.2 here. This is in an advanced version. This is in an advanced version. That warning it will give, which means that either the package is the older one, you might search for the new package for the better performance or for the easiness of our work, or you may update our R software. Say for example, here I am using that 1.2, so I want to update my software to 1.3. Fine. So that's the one. And with let me go ahead with my data once again. So it is with my data. it is my data. Come on, yes. Okay, it's with my data. So it is GHRT dot correlation. See, if you type this, automatically the performance analytics, that one will come. Correlation. I'm giving my data. I want to do that for my data. Program equal to, I make it as true. And PCH is the point size is equal to 19. If we have not given comma, actually we can give our method of correlation also. If you have not given anything, then it will take automatically as a Colp-Poisson coefficient of correlation. In this chart, in this chart, you the same data for the same my data, you will be getting this chart for every variable you will be getting. For example, MPG with the MPG, this with this, HP with the HP, like that. The histogram with the density plots you will be getting, along with the correlation coefficients, scatter plot, smoothed line for everything. So that's why I told you. See here, what I have done earlier. I run this one with the car plotter. I told you the car plot is a very good one, and we are getting this correlation matrix. And now I run with the chart of correlation. With the chart of correlation, I am getting everything in the performance analytics package. So which package we have to use? It is depends on your requirement. Whichever you find it is suitable for you, and you are going to explain in your research article, then you have to use that one. You have to use that one. Fine. So for this simple work, how much we struggled earlier to write the program is the headache, but still that happened. What to do? Okay, let me save it. Fine. Let's create another variable with the R norm. Say for example, I'm writing some y. It doesn't matter because yeah, use R norm. I'm generating 20 values with the standard deviation equal to 1, with the mean is equal to 0. You could observe here I have written mean and standard deviation, whereas here I am writing standard deviation and mean. So if you write this parameter, these variables, then automatically this will take mean equal to 0 and standard deviation equal to 1. You can write the same command like this also. If you write like this without giving these names, standard deviation equal to, mean equal to, if you give like this, this will take in this order, sorry, in its order. What is its order? It has to generate 20 numbers, mean is 0 and standard deviation is 1. The number of items, mean and standard deviation is the usual order of R norm. This will take its own order. Its own order. You can change the order provided you have given this part. So let me run this while, and I'm creating another x. I want to create another x, y plus R norm. R norm. Again, I want to take 20 values, right? 20. I want to change my standard deviation, and let us take the mean same. Doesn't matter. Mean is 0, so it is created. You can see I'm making a linear increment. I want to create a regression line. The command is LM, the linear model. It is with the LM linear model. It is Y with X. So here you can get, I'm predicting the Y values with X, and this is the model. So the equation of this is 0.9237 this into X plus because it is plus 0.01757. This is the value of y. This is the value of y. So if you are writing mathematically, this will be our answer. This will be our answer. Fine. You can go for summary of LM of y with x. And here it is, you can get the entire summary. You can get the entire summary, the minimum, median, the 5-number summary, minimum, maximum, first quartile, second quartile, and third quartile, median, the coefficients, the estimates, the x-intercept, the x and the y-intercept, the standard error, the probability, right? And here the significant codes, multiple R squared and adjusted R squared. Actually, the R square value we will get as the positive, the square of the coefficient of determination, and this R square value usually used to express the variation in terms of the percentage, the relationship in terms of the percentage, but that will not look perfectly because what actually a good R square value? What actually a good R square value? Because depends on our particular grouping variables, we have to adjust our R value. Actually, that is what it is giving over here with our error. With our error. Here it is giving the p-value. This is the p-value of the model. This is the p-value of the model. We have to take it from here. We have to take it from here. Even if here we can take, because I have generated 20 numbers from here. It is 20. So totally we have 20 values. So 20, 2 here I have. So it is with the 18. 20 minus 2 columns I have. Now, what actually good R square? Then see, sir, if you are saying this R square value is not that much, people are running behind this R square value, then what may be the good R square value? If I have a 0.93 as the R square value, whether my model is good? No. There is no such a meaning. The R square value is not interpreted in such a way. Even for a very good model, you can get a least R square value. A least R square value. This R square value will give you the percentage of variation, whereas this will not showing you the predicting power of your model. The predicting power of your model. Say for example, even R square value of 0.5 can be considered a much stronger contribution. Yeah, you see, if you go for mutual funds, these kind of R squared value, even with the 0.3, they will be saying, yeah, it's a very excellent one. You can buy this fund. So it depends on the situation, definitely. And in case of higher R squared value, we have to repeat the test for our data to check whether the R square has huge variations or it has the less variations. We can try changing the samples in order to get the perfect R square value. What else we can do for R square? That's it. That's what we know. Okay, then you see, if you are saying like this for R square, then how can I know? So it is for fitting, right? So let us plot that let us plot that x comma y. Let us plot that x comma y. See, this is the x comma y value, the raw data plot. Even we can say the scatter plot of that x and y. You can create the line. You can create the line. AB line is the AB line means that will give you the line, that will give you the straight line. No, that will give you the line. Whereas you want to create that for your model. So LM of y with x. Now you will get this. Now you will get this. Now we can see the variations over here. See how much deviated our actual data from the fitted line. So from here we can analyze whether this much of difference is admissible or not. There are two extremities here. One point is here and another point is here in the top right. In the top right. So we have to deal these two. We have to deal these two separately. We have to deal these two separately. Fine. So we have to concentrate on that data. Whether is there any typo error, whether that data is reliable, or whether it has to be removed or it has to be replaced, or we have to do something else for that data. Okay. Now, let me take it as a fit, some name, fit of LM y with x. Let me take some name. Now let us plot third values of my fit and residual value of my fit. Residual value of my fit. See, from this data we can get, see, earlier in the fitted, that is the earlier one with AB line, that one we could see only 2 points. We can observe only 2 points are deviated from the fitted one. Whereas after fitting this with the residual, that is with the errors, you can see once again the 0.8, the top one, the residuals, and here 2 values, whereas here also there is one more value, but we have to decide whether the third point has to be accepted or it is not accepted. This ID of fit QQ norm. QQ norm is the quantile normal plot for the residual fitting. So what I have done, we have taken the residuals and we have making it as a quantile plot, and I'm going to write the QQ line also. QQ line. If you write the QQ line for your the residual of your fitted values, then you will get that line. Once again, these 2 points are deviated from yours, and in fact this distribution is normally distributed, that is approximately normally distributed. Okay, so let me make it a simple one. See, I'm having some x values. Let me type it. Just some values. Am I right? 1 2 3 4 5 6 1 2 3 4 5 6. Yeah, it's okay. So what you can do, just first we are going for the plot of y. You will get that uh, scatter plot, and then you can fit something. In the fit we are using for the linear models. It is with y and x. The model is fitted, and then you can go for the print fit. Even you can get the summary of it. Then AB line of it, we discussed it, and then the residuals we discussed it, residuals of it. Fitted values. The fitted values can be displayed separately also. You can find the differences, between, even you can find the errors also. Fitted between the fitted value and the value what you have. Okay, so these are the items we discussed. Even we discussed the chord plots also. Finally, I just want to tell you very few items. One is few review research papers, research paper reviews was collected. It is to share that with you, where we will be doing the mistakes usually. So here, let me do like that. If the variable, without finding the correlation, if we are doing analysis, or if you are writing the paper, usually that will not be accepted, though we are going to write correlation is equal to 0.7 or 0.6, this is highly correlated, less correlated, like that, because that is the one used to tell us whether that correlation, that is that much of correlation is effective or not, whether we can include that variable in the analysis or not, then what kind of effect. Say for example, we have discussed the 3 parameters: medication, exercise, and diet. Suppose the diet has a very huge correlation, then what we can say, that will contribute to the reduction in the BP much. So that kind of things we have to analyze. So leaving the highly correlated variables is not advisable. So whenever you are having a huge set of data, try to have the correlation matrix, try to find the interrelationships between them. And even before starting the t-test or the f-test or ANOVA, even for correlation also, I told you the assumptions. So if the assumptions has violated, definitely you will not be getting your answers. We will be getting the homogeneity in the variance. See, for example, one student has done a research work in the angular rotation. And they repeated the tests, and they did the ANOVA, and they find yes, it is statistically significant. There is a difference, everything they have done. And when they rechecked, that correlation become high, the angular rotation become 3 times of its variance, that is by changing the training and testing data set, right? And they were getting the very entirely opposite result. The issue over there is they have not done the normality test. We have done the QQ plot, quantile plot, even histogram. Histogram used to actually why we are using histogram? It is not just to draw a graph, but it is to analyze the normality of the given one. It is to find the extremal interval immediately. That is the objective of the histogram. In no time we will be getting the idea about our data, whether where our maximum, that is the average, will be centered. We will be getting an overall picture just by drawing the histogram. Okay, so what is the problem here? They violated the assumption of the normality, and hence that is not possible. Okay, so the next one, this we have done. The correlation misinterpretation. See, if we are doing two separate groups, we cannot mix that two separate groups. We have to find within our group A 2 variables, group B 2 variables. Like that we can do. After finding the correlation, once again we are finding the correlation, means that will become the redundancy. It is like finding the average of the average to find the combined mean. That become the wrong interpretation. Okay, there is another one, casuation. Another one is casuation. Usually this correlation will give you whether is there any effect or not. That's all. It will never say which variable contribute the effect on the another variable and how to rectify. No, it will not give. So if you find the correlation and we are getting a high 0.9495 of correlation, and we are telling, yeah, it is a very highly correlated, the relationship between those two is perfectly right, then it is not. Say for example, I have the habit of buying the pens, pen, right? Writing pens. So in the first month I bought 5 pens. In the second month I bought 10 pens, and in the 12th month, that is I am calculating for 1 year. In the 12th month I bought 500 pens. In the 12th month alone, in only 1 month I bought 500 pens. And now my son is having the habit of taking more chocolates. In the first month he took, after reaching here, he took only 5 chocolates. In the second month he habituated 15 chocolates. In the third month he habituated, per month he is taking around 50 chocolates. In the 12th month he is taking around 350 chocolates. If you find the correlation between these two, this will be showing a very high correlation of 0.98 or 0.99. So because of that, we cannot say, since I am buying the pen, he is taking more chocolate, or it is because he is taking more chocolate, I am buying the pen. So this will not give any such a relationships. So if you are writing a research paper, we cannot come to such a type of conclusion. And the assumption checking is more important. Actually, it is one another data. I'm sorry for that redundancy. We completed these regressions. Limitations, yeah, the assumptions we already discussed it. Yeah, I told you that homoscedasticity and heteroscedasticity, right? The error terms must have the constant variance. The residuals and the errors, we calculated that errors, right? Those errors should have the constant variance, and this is called homoscedasticity. And if it is non-constant, that is called heteroscedasticity. So if you have such a terms, it should be normally even our error terms also normally distributed. That is why we are giving more and more priority to the normal distribution. If you start studying probability, immediately they will ask you normal distribution. They will ask all the probabilities, that one, this one, everything. Because everywhere is normal distribution, the normal distribution we have to check. Even in order to check the normal distribution, normal distribution, we have other tests like Sharpio test, Kolmogorov test, that and all we have. The next. So there are some disadvantages. Let me share that with you. You can do that. Now, the finding the average is easy or not? That's the question. Because we started from arithmetic mean. Now, at 2020, they have given one. I'm sorry for the slight blur. They have given this data, and it is with Ms. Colleen Huber. He is a doctor in profession, I believe. She wrote in a blog. She has given this data from 2000 to 2020, and she calculated the deaths in US, and 2020 she calculate 2020 also she has calculated, and the average number of deaths become same almost per week, become same almost. So she is claiming there is no pandemic at all. Who told you there is a pandemic, since the number of average number of deaths are same? This is even all of us knows this is an awkward analysis, because in all the rest of the years it is with the 52 weeks, and here we are calculating only for 32 weeks, still 20 more weeks to go. How can we calculate this average, and how can we conclude immediately there is no pandemic in 2020? So that's the first one. That's the first one, the very crystal clear one. The second one is, if actually that the data downloaded from CDC, that is she has given data, right? That data is downloaded from CDC, and after drawing the graph, it is showing this curve. This is a perfect this is a perfect trending curve. It's a I'm not getting the name immediately. A seasonal. It is a seasonal curve actually. See, in the third quarter it is less, third quarter it is less, third quarter it is less. In the fourth quarter between 1 to 2 it is more, here it is more, here it is more. So it's showing the seasonal variation. So if there is a seasonal variation, then we cannot find our usual average. That is the special average called the time series average. So this is the dengue data, the dengue deaths in India, whereas this is also the disease death only, but you can find the average. That is, you can find the arithmetic mean, because it doesn't show the seasonality. It doesn't show the seasonality. Okay. Now, here, file, new file, markdown or markdown. File, new file or markdown. This you can open. After opening, I am writing some inferential statistics with the R workshop on. So you can generate in 3 ways: HTML, PDF, and even Word also. I am giving PDF, and I am giving OK. So automatically this will be this page will be shown to you, and say that a title, name, that and all will be here. You can type, you can use your LaTeX, you can use your LaTeX code, you can use your commands, the R commands, and everything here. And you can click night. I'm sorry, I have to save this. Okay, let me night it. Wow, where it is, line 81. Should go line 81. I don't know what is the problem in line 81. Fine. So let me go ahead with this. So I am just saving. The command name is some ABCD. Okay, that's enough. ABCD, and let me night it. So after making this night, actually here this is the button night. You can create the PDF file. You can create the PDF file. I'm sorry, it's doing somewhere. I want to drag it actually. Yeah, let me make it a little big. Yeah, such a graphs and everything that you can do from here. What you can do, say for example, you can copy paste your command. You can copy paste, just copy pasting. So whatever we are doing, say this package is not available. Okay, so just you can copy paste your command. You can copy paste your command. Instead of this, I'm giving this one, and let me go for the correlation. Then you will be amazing for that. Where is it, correlation? Yeah, here it is. Same issue arises in the last one also. There should not be anything. Run all. Come on. Yeah, thank God. See, you can create wonderful. Actually, R is highly appreciable for its charting capabilities and the documentations. So you can write your documents. You can create all these diagrams. You can change the size of the diagrams also. Just I copy pasted, right? So I haven't given any customization. So it is showing so. Even you can type a mathematical symbols, that and all also with this R markdown. Even you can create the PowerPoints also with R.